All right, so the next thing I'd like to look at then is what happens if we've got a more complicated kind of motion in which the slope is of the x versus t plot is changing. And we might wonder, well, what happens there if we've already equated the slope as being the velocity? Then if the slope changes, I think it is a natural conclusion to make that the velocity will change. And so how would that look? Well, it would no longer be a straight line plot of x versus t. And so let's say that we have our system set up in such a manner that our fan cart then would represent our mass, and we turn that fan cart on at time equals 0, and then watch what kind of motion it experiences. So if I let go of this thing, at time equals 0, it starts to pick up speed. Okay? And associated with that then, we actually can show that if this is a parabolic plot, that the change in the speed is uniform. Not meaning that the velocity itself is uniform, but that the rate of change of the velocity is uniform with a parabolic curve. And so here, in this kind of a plot then, let's say that we start at time equals 0. And now notice here also that in your math classes, a lot of times you'd extrapolate to negative values for the time. But we tend not to do that quite as much in physics classes because the domain of our function is usually defined in such a way that for convenience, the time is just, we'll call it 0 at time equals 0. And so that's when we start our stopwatch. Okay? And so then at time equals 1 second, let's say here that x equals 1 meter, time equals 2 seconds, x might equal, say, 4 meters, x equals 3 seconds, time equals 3 seconds, x would be 9 meters. So this kind of a relationship then would look like x is equal to 1 times t squared. On the other hand, if this were a 2, so after 1 second we've gone 2 meters, after 2 seconds we've gone 8, and after 3 seconds we've gone 18, then this relationship would look like x equals 2t squared. Okay? And so then this is a way then of representing the displacement versus time for an object in which the velocity is changing. Now how do we know the velocity is changing? Well, we can look up there at the data projector and we can see that if we take the slope of the tangent line at different points, which we could call here t1, t2, and t3, that the slope of the curve is getting bigger. But remember that the slope is just the velocity. And so what that's showing us here is that the velocity in this case is increasing, and so therefore we can define an acceleration in a way that measures the change in the velocity. And so how would we do that? Well, first, let's see how we could get an expression for the velocity from knowing that x equals 2t squared at any given value for t. In other words, how would I know what the slope of the tangent line is at t equals 1 second, or t equals 2 seconds, or t equals 3? I can see here graphically that the slope is increasing, and that slope is the velocity. But by how much is it increasing? Well, you took a calculus class before this class, and what that illustrated at one point was that the, let's go one more here. We saw at one point was that the slope of a tangent line can be given in terms of the rules for calculating the derivative. Okay. And so that derivative then, relationship, just looks like if x is a t to the n, then dx dt is a n t to the n minus 1 power. So in this example, x is a little more complicated function than the one that we were just looking at, 5t cubed plus 3t squared plus 2t plus 1. And so if we were to write dx dt then, we would take the power of t in that first term. That'd be 3 times 5 is 15 times t squared plus 2 times 3 is 6 times t to the 1 power. And then the 2t term is 2 times t to the 1 power. So that's 2 times t to the 0, basically, 1 times 2 times t to the 0. And then the constant term is just 0. So that gives us an expression for the velocity as a function of time. Now, why does that work? Well, the reason that that works is that essentially what you're trying to do is take the slope of a tangent line, and so you take 2 points that are fairly far apart, and then you just shrink the distance between those 2 points until essentially taking the slope of the chord that joins those 2 points is essentially the same thing as taking the slope of the tangent line. So we can see here that if I draw a chord between A and F, that's not approximating the slope very well. But as B starts getting closer to A, we see that the chord is getting closer and closer to representing the value for the actual slope. And if we go over here and we bring B in closer and closer and closer, and then we start to approach the actual value for the slope of the tangent line at that point. And so we can write this then by saying that in the limit, as the distance between those 2 points, and therefore the change in time goes to 0, then delta x delta t is equal to dx dt. And that is our equation for that follows for determining the derivative of the function. Okay. So with that idea in mind, we can go back to this simpler example, x equals 2t squared, and we can now calculate the velocity. That's going to be the derivative of x with respect to time. So that will be 2 times 2 is 4 times t to the 2 minus 1 power is t to the first power. So it's v is equal to 4t. So at time equals 1 second, v of 1 would be equal to 4 times 1, or 4 meters per second. Here at this point, v of 2 would be equal to 4 times 2, or 8 meters per second. And at this point, v of 3 would be 4 times 3, equal to 12 meters per second. So we can see then that as time increases, the change in the velocity remains the same. We're increasing by 4 meters per second every second. Okay. And so we can go one more step with this and find the acceleration. The acceleration then is equal to the derivative of the velocity with respect to time. And so how can we determine this? Well, we need to now plot up what the velocity versus time function looks like. So this is v, that's t, and the slope here of v versus t is 4. Okay, and so it follows in a very analogous way to the way in which we defined the velocity as the derivative of the displacement. We can say that the acceleration is the derivative of the velocity. And if the velocity versus time plot is a straight line, then the acceleration is constant. Okay, so there's some confusion oftentimes by what we mean when we say the acceleration is constant. Does that mean the velocity is constant? No. It means that the velocity is changing at a uniform rate. So if you're looking, say, at your speedometer, and the speedometer goes from 0 to 60, but it does so in a smooth manner where it's covering the same amount of velocity span in the same amount of time, then we would say that the velocity is constantly changing, but it's constantly changing at a uniform rate. And so therefore we have a constant acceleration. Now the same kind of problem is true if I were to change my direction of motion to vertical. Okay, so let's do that by accelerating this pen under the influence of gravity. Okay, so if I take this pen, I throw it up into the air, and then it comes back down again. How is that different, do you suppose, from taking this mass and pushing it this way? The object comes to rest and then starts to speed back up again in the negative direction. Okay, so it's slowing in the positive, then speeding up in the negative. Okay, how is that different from this problem where I take a pen, I throw it up into the air, first it's slowing in the positive and then speeding back up in the negative? Answer is, well, the value of the acceleration is probably different. But the actual mathematics of the motion and the way that we would plot this motion is going to be the same in either case. And so let's just see that by drawing a plot of the velocity versus time for this problem. Okay, so I take this pen, throw it up in the air. As time goes on, the velocity goes from some initial velocity to some final velocity of 0. This is on the way up. The velocity is getting smaller. Then finally the velocity is 0 there. Then on the way back down, it starts to speed back up. By the time that it's gotten to the point that it started from, it's now moving, turns out, with an equal velocity in the negative direction. So if we were to plot the velocity versus time for this, it would start out positive, it would slow down to 0. Now what's the acceleration when it gets to this point? Well, the acceleration is the same all the way through, because this thing is first slowing in the positive and then speeding back up in the negative. So the acceleration is a vector that's acting to oppose the initial velocity. But then once the velocity vector starts pointing in the same direction as the acceleration, then it starts to speed it back up. So it would look like this to 0, and then it would continue to follow that same slope all the way down. And now, for an acceleration due to gravity, we can say that this number is a 9.8 meters per second every second. Or another way of writing that is 9.8 meters per second squared. So that's just a shortcut way of writing the acceleration units. But I think that this particular form for the unit expression is perhaps a little clearer in that it shows that the velocity is changing by 9.8 meters per second every second. But meters per second times second can be abbreviated to be meters per second squared. Now sometimes in a class like this, what we'll do is we'll round that off to 10, just because it's easier numbers to work with. So if we say that the acceleration due to gravity, in this case, is minus 10 meters per second squared, because it's pointing in the opposite direction from the direction that we could consider to be the positive direction, then what this would represent then, if the initial velocity, say, were 50 meters per second, is that after 1 second, we would be going 40. Pt equals 1. Then after 2 seconds, we'd be going 30. So this is the slowing in the positive direction. We throw the thing up, but the velocity is in the opposite direction from the acceleration. And so that causes what we call a deceleration, or a negative acceleration. Okay, and so after 2 seconds, you'd be going 30. After 3 seconds, you'd be going 20. After 4 seconds, you'd be going 10. After 5 seconds, you would stop moving. And so you would reach the peak of the path. And that would be a velocity of 0. But notice that the slope of this curve is minus 10. Okay, and then from there, after 6 seconds, you would now start to speed up in the negative direction. And after 7 seconds, you'd be going minus 20. After 8 seconds, you'd be going minus 30. After 9 seconds, you'd be going minus 40. And after 10 seconds, you'd be going the same speed that you were when you started, minus 50. And so first you're slowing in the positive direction, then speeding back up in the negative direction until you get to the point that you started from. And at that point, you're going the same speed, but in the opposite direction. And so that, in fact, is the same thing that's happening with this air cart. If I let the air cart want to push this way, you can see that if I just let it go, it'll push that way. That's like gravity tending to pull down toward the center of the earth. So if I move in the opposite direction, first there's a slowing in the positive direction till we reach 0, then a speeding back up in the negative until we've reached the same speed that we started with. So this plot then, although the slope would be different for the air cart, is exactly the same plot that we have for the pin that's being thrown up into the air. But in either case, we're dealing with a parabolic function. How do we know that? Well, if we write x is equal to at squared, then dx dt, or the derivative of x with respect to time, is going to be 2at. And then that's your velocity, v. So we can either write it as the second derivative of x or as the derivative of velocity. That's just equal to 2a. And so that's a constant. So constant acceleration is the same thing as a parabolic relationship between x and t. In other words, it's a polynomial function raised, a second order polynomial function, corresponds then to a constant acceleration. So what if we had an acceleration that was associated, for example, with a third degree polynomial? How would that work? Well, in that case, the acceleration would be variable. It would change as a function of time. Because then the velocity versus time plot would no longer be a straight line. So if we go to second degree polynomial, of x versus time, we have a constant acceleration. And that's the same thing then as a linear increase in velocity. But for a higher degree polynomial, we have a variable acceleration. Now with a variable acceleration, the motion is a little more complicated. Let's look at an example. Now in this case, let's set up our one-dimensional motion to be vertical, like maybe a rocket ship or something. And let's say that for this problem, y is equal to 5 times t minus t cubed. And let's try to find out some important aspects of the motion of this object. So first of all, let's try to find the velocity. So if we want to find the velocity, then v would be the derivative of y with respect to time. So that would be equal to 5 minus, and then here, this would be 5t cubed, and so we'd have 5 times 3 is 15t squared. Okay, so that would be our velocity as a function of time. Okay, and so can you see then that this object will initially tend to want to move in the positive direction? So if I start out here at time equals 0, it'll have an initial velocity. Because at time equals 0, v of 0, which is the initial velocity of the object, is going to be 5 meters per second. So we could call this v naught equals 5 meters per second. But I think you can also see here that as time goes on, the velocity is going to tend to want to go to 0 because this term is negative, and that's going to take away from the 5. And then it's going to start wanting to speed up in the negative direction. So if that's the case, then this thing is going to turn around, and if the ground doesn't get in the way, it's going to start speeding up more and more in the negative direction, because this term will dominate over the 5. And so let's just, for the purposes of this example, let's try to find the maximum height that this object reaches. So what's our technique going to be here? Well, we're going to need to know when the final velocity is 0. And once we know when it's at 0, then we can evaluate and find y max. Okay, so that is going to be my strategy then for solution, is that I'm going to look at what time corresponds to the velocity being 0. So that's the slope of our y versus t plot, and we want that slope to be equal to 0. So 0 then would be the velocity, 5 minus 15 t squared. That would give us 15 t squared equals 5, or t equals 5/15, which is 1/3. So t would be 1 over the square root of 3 seconds. Or that would be equal to 1 over 1.73 seconds. Then once we have that expression for the time, that's the time that can be plugged back into this expression to find y max. So y equals y max when when v final is equal to 0. And that is when t equals 1 over root 3 seconds. Okay, so now I can take and evaluate this function when time equals 1 over the square root of 3. So that gives me y max equals 5 times 1 over square root of 3 seconds minus 5 times 1 over square root of 3 cubed. And so that then is going to be equal to 5 over root 3 minus 5 over 3 root 3 seconds. And so clearly then, this we could put a lowest common denominator of 3 square root of 3. So this would give us 5 times 3 minus 5 over 3 square root of 3. Or 15 minus 5 is 10 over 3 square root of 3. That would be in meters. so that gives us a final result of 1.92 meters. And so that then would be the maximum height of the rocket, let's say, or whatever this was, that had that third order polynomial expression for y. And then finally, we could calculate what is the acceleration when it reaches the maximum height. So what do you think it would be if the velocity is 0? Well, a lot of people would say 0, but remember that that's the velocity that's 0, not the acceleration. The acceleration is variable and will change from moment to moment. So the acceleration then is not 0 in general when the velocity is equal to 0. This is just a point at which the velocity is changing sign from positive to negative. But the fact that it's doing that tells us that the acceleration must in fact be non-zero in order to create a velocity that is 0 at that moment. Means that it was positive and now it's becoming negative, and so it's changing therefore. And it can only change if there is a non-zero value for the acceleration. So the acceleration we can get then by taking the second derivative of y. We had the expression for the velocity before. Remember that that was equal to 5 minus 15 t squared. So the acceleration would be the derivative of this, which would be 2 times 15 is minus 30 t. Okay, and so this is the expression for the acceleration in general. It's always going to be negative and is going to be proportional to the time. And so at a time that's equal to 1 over the square root of 3 seconds, we have the acceleration is minus 30 times 1 over square root of 3. Which is 17.3 minus 17.3 meters per second squared. So you don't want to just have this knee-jerk reaction and say that when the velocity is 0, the acceleration is 0. We see that in general that will not be true.